Hello everyone, I will talk about Strudel, a map model validation approach, and apply it for the validation of SARS-CoV-2 structure. I will start with a question. What should an amino acid residue look like in cryo-EM? This is an important question because the answer affects how we interpret and validate the cryo-EM data. Here are 6 map regions of a phenylalanine isolated from different maps at around 2.5 angstrom resolution. To which of them would make sense to compare a map region where we suspect to have a phenylalanine? Well, none of them is optimal because they are affected by high level of noise. But if we have several images of the same thing, then by careful alignment and averaging, we can increase the signal-to-noise ratio and produce a better quality image. In this case, we have averaged 80 images. It is easy to notice that the resulting image is much less noisy. We applied this approach to produce canonical motifs for all amino acid residues in rotamer conformations at different resolution bands. To do that, we first needed a way to locate the map regions belonging to individual residues. For that, we used the atomic models. Obviously, the result is highly affected by how well the model is fitted. Unfortunately, many of the available models are rigid body fitted or not optimally refined. Also, cryo-EM is a fast-growing field and the refinement tools are improving constantly, which means that many of the entries can benefit from the refinement using the latest versions of the refinement programs. To make sure that we have a well-fitted model, we developed a pipeline for automatic models refinement using RefMac, Phoenix, and map-motif programs. This plot here shows a map model Fourier shell correlation change after the refinement for around 2000 entries. If the correlation improved, then it's colored in green. If it got worse, in red. As you can see, most of the models improved. Next, we impose the following selection criteria to exclude low-quality models. Ramachandran favored more than 90%, Ramachandran outliers less than 0.5%, clash score less than 20, and average allele space map model correlation more than 0.7. This yielded almost 1200 models and maps which were suitable for map-motif mining. To do that, we first chopped all the models and the corresponding EM maps into individual amino acid residues. As I mentioned earlier, it is really important to average images of which depicts the same thing. In the case of amino acid residues, this means that they should be in the same conformation, so we needed to split the chopped maps into conformation classes. For that, we used the Richardson rotamer library, and here you can see the rotamer classes for the phenylalanine. After classification, we superimposed and averaged the maps of each class. For that, we first superimposed the atomic models, then we applied the same transformation matrix to the corresponding maps, and did an additional map-to-map fit. This gave us the motifs for each amino acid rotamer. Here are shown the motifs for a phenylalanine and a glutamic acid rotamer in several resolution bands. The grouping into resolution bands is done based on the resolution claimed by the authors in the incoming entries. You can see how the shape changes with the resolution decrease. At this stage, we had a library of amino acid map motifs generated for different resolution bands. They can be used for various purposes, but we were most interested in the map model validation. For that, we propose a score. We call it Strudel score, and is calculated in the following way. For a target residue, we isolate the map around the atomic model and calculate map correlation coefficients with each motif in the library, which reflects how similar is the isolated map to each of the motifs. Now this generates a large amount of numbers, which is quite difficult to interpret. To facilitate that, we developed a GUI which runs as a Chimera X plugin. It looks like this, and I will briefly explain what it shows. This section here is for the input data, map file, model file, and the resolution of the library against which the scores were generated. Below is the per-chain scoring summary, the average score, the closer to 1 the better, and the percentage of outliers. The plots on the left shows individual residue scores. If the residue scores well with a motif of the same type, then only a green dot is shown. If there is a motif of a different residue type which scores significantly better than the two dots are shown, a red dot for the best scoring motif and a green dot for the same type motif. Upon clicking on one of these dots, another plot is shown on the right. On this plot, we have the scores with the motifs of each residue type. The score of the same type motif is shown in green, and all others in red. In this case here, we can see that it scores the best with the motif of the same residue type. Now I will show a few examples to illustrate how a good scoring residue and an outlier look like and how do they compare with the library motifs. First case here, it's a good scoring residue, and we can see that the library motif fits very well the map region of this residue. The second case, it's an outlier, and the library motif is quite different to the map around this residue. So you can see that there is quite a lot of unexplained map. The next case, it's again an outlier, and it's an opposite situation. So there is a missing map when we compare the library motif and the region around the residue. Here is how the Strudel score plugin looks like within ChimeraX program. The reason why we wrote it as a plugin is to be able to use the model viewer. So now when we click on a specific residue, it will be shown in the model viewer part of the ChimeraX program. I hope I managed to give you an idea of how this program works. So now I'll move to use this program to analyze the validation results for one of the early SARS-CoV-2 related structures, the EMD 30178. So if we look at the validation results, we can see first that the chain A has quite few outliers, so it's 2.7% outliers, and which means that most of the residues score best with the map motifs of the same type. Like in this case here, it's modeled as a tyrosine, and it scores best with the tyrosine motif. Now the labels on the right plot are clickable, and if you click on them, it will show the best fitting motif of this amino acid type. However, when we look at the C-terminal end of the sequence, we see an entire stretch of outliers. Let's try to figure out what is happening here by going through some of the outliers. So one of them is the residue 907, which was modeled as a leucine, but it scores quite poorly with a leucine. Instead, it scores very well with a tryptophan. And if you look at the structure, see that there is quite a poor match between leucine and the map here, because there is quite a few unexplained map. So if we display the leucine motif, we can clearly see that it's quite different from the map in this area. Now if we display the tryptophan motif, which scored top in this case, you can see that there is quite a good match. So it might be that we have an error here, and it should have been modeled tryptophan instead of leucine. Moving forward to another outlier, we see a similar picture. So for the residue 912, it was modeled as a threonine, but it scores quite poorly with the motif of this type, but it scores really well with aromatic residues like phenylalanine, histidine, and tyrosine. If we display the threonine and phenylalanine motifs, we can see that the threonine motif explains quite poorly the map in this area, And the phenylalanine fits well and explains most of the map here. Now I don't have time to go through all of the outliers, but I can say that after a careful examination and comparison with the sequence, we could determine that there is an register error here with a shift of 9 amino acid residues. After some time, the authors updated the model and we ran Strudel validation for it as well. As you can see, most of the outliers are now gone, and after comparison with the previous results, we could see that our hypothesis that there was a 9 residue shift was confirmed. And here is one of the residues which previously was a strong outlier. You can see that now its scores top and it's a perfect fit with the map. The Strudel score software and the map-motif libraries are not yet publicly available, but we hope to do that soon. So both the software and the libraries will be available through CCPM suite. Also, we will publish the libraries on the EMDB website. As for the visualization plugin for Chimera, it will be distributed through the Chimera X toolsheet. Also, we will set up a server at EMDB for the Strudel score calculations. With that, I would like to thank all the people who worked on this project, my supervisors, Arden Patwarden and Gerard Klebeck, and the collaborators from MRC LMB, Garib Murshudov, Michael Tikak, and Ranganova Shamangi. Also, I would like to thank Tom Goddard for the help with Chimera X, and Paul Adams and Jane Richardson for the help with Phoenix and all the CCPM team. Also, I would like to thank BBSRC and Humble for financial support of this project. Last but not least, I thank the organizers of this event for the opportunity to talk here. Thank you.